Welcome to the sixth of 8 sessions and to today's session, From Systems to Downstream Engineering. I am your host, Ray Barton. I'm on the board of the INCOSE Canada chapter. Welcome, INCOSE members, and to all non-INCOSE members as well. It's also worth noting we have attendees from around the world who are taking in today's information session. It's a great honor to have you. To the 6 INCOSE chapters and to the sponsors, Smith and Nephew, I extend a very special thanks for making this series possible. The Great Lakes North region have contributed both time and money to bring about this series of lunchtime learning. It is a great example of what we can do to accomplish, or what we can accomplish when we take initiatives to work and collaborate together to further our professional development and to hone our skills in model-based systems engineering. Next slide. As already mentioned, this is the 6th of 8 Lunch and Learn sessions. Each session is intended to build on the previous sessions and to provide you a full life cycle and end-to-end view of model-based systems engineering. The goal is to provide you the knowledge to be able to select and adapt the development and implementation process to meet your unique needs. The next 2 sessions, the 7th and 8th session, are on January 12th and 26th, Wednesdays at 12:30 Eastern Standard Time, 11:30 Central Standard Time. There is a link we'll provide later where you can register for those sessions now. Organized by INCOSE volunteers from the participating chapters in collaboration with Dr. Douglas, our distinguished speaker and lecturer. This is all brought to you free, thanks to funding from Smith and Nephew and the participating chapters. Next slide. All the sessions have been recorded and can be viewed should you have missed a session or would like to view a session again. In addition to the recordings being available on the INCOSE GLNC regional website, you can refer to Bruce Douglas's YouTube channel. Following the completion of these lunch and learn sessions, planning has now started to organize an MBSE challenge team program. We're expecting to be able to provide hands-on tools for the team to take on a project and build a model. Mentorship and guidance will be provided to assist in the learning. Many of the details on this offering are still being worked on, so stay tuned. We hope you will participate. It is unfortunate the INCOSE GLNC Regional Conference on November the 30th to December 3rd had to be postponed due to the fast evolving next wave of COVID and its variants. The new plan for the conference are presently being worked on. You'll have to stay tuned to find as to when it will be offered. Next session, or next slide. So INCOSE is a world-leading professional engineering organization focused on systems engineering and systems thinking. Systems thinking being the base for all the work being done within systems engineering. It has an amazing array of resources and products free to members. Networking with like-minded professionals is the biggest benefit of being a member with INCOSE. One of the most important ways to engage in a subject and topic of interest to you is to participate in one of the working groups. Next slide. So INCOSE has global reach with countries in 3 global sectors. There's the America sector covering North and South America, consisting of 48 chapters. There's Europe, the Middle East and Africa sector consisting of 16 chapters. Then there's the Asia Oceania sector consisting of 9 chapters. So you can see the global reach INCOSE has. Next slide. So of the 12 GLNC, the INCOSE chapters, 6 are collaborating on this Lunch and Learn series. While the Great Lakes North Central region consists largely of the chapters in the Northern Heartland chapters neighboring the Great Lakes, it includes the Canada chapter, which stretches coast to coast from east to west. Virtual conferencing has greatly facilitated collaboration and offering joint programs. The Canadian chapter is very thankful and grateful to be able to actively participate in the Great Lakes North Central region. They have a great set of people that have provided enormous help to the Canadian chapter. Next slide. So this slide shows the CAB members, which are corporate members, and steer INCOSE direction, products, and content. Corporate members span industry, government, and academia. Employees of CAB companies can register as an associate INCOSE member at no cost to them, which provides full access to INCOSE information, resources, and services. If you work for one of these companies, be sure to take full advantage of this benefit. Next slide. Working groups are initiatives focused on a number of areas in systems engineering. 5 of the 55 working groups are associated with Agile MBSE. They are highlighted in red. Consider taking an active role. I'm confident you will find your involvement meaningful and rewarding, and keep you up to date on the latest tools and techniques. Next slide. For more information about INCOSE, visit their website. It includes how to join as a member, but has much more information as well. Next slide. From the last session, session 5, the book drawing winner was Paul Miller of the Three Rivers chapter in Pittsburgh, Pennsylvania. Another random draw will be done today at the end of this session for the next winner. Next slide. So without ado, I want to introduce Bruce Douglas. Dr. Bruce Douglas is a renowned professional, consultant, and evangelist on a number in a number of subject domains, including UML, SysML, embedded systems, systems engineering, and Agile MBSE. He has seen the evolution and growth of methodologies for the development of critical systems, real-time systems, embedded systems, from their infancy to where they are today. He was formerly chief evangelist at IBM and currently the senior principal Agile systems engineer at the MITRE Corporation. He is author and been co-author on more than 20 books. Please join me in welcoming Dr. Bruce Douglas.
Thank you, Ray. Let me share my screen. So welcome, everyone, to this session number 6, that has to do with the handoff from system engineering to downstream engineering, which includes, software, electronics, and mechanical engineering. This is one of the most common topics I get asked about. How do I do that? How do I move from my MBSE model to downstream engineering? So in this talk, I'll talk about what I do, some of the rationale behind why I do it. And I'll be kind of prescriptive about the steps involved. And if you have questions, you can post them in the chat, and we'll take a look at the questions then towards the end of the talk. So this is the Harmony Agile model-based system engineering process, of which I'm the author. In that, there's a number of steps, and you see it's cyclic. So you can define some requirements and do some analysis and architectural analysis and some architectural design. You can hand off and then do some more analysis. So this is an iterative process for doing the system engineering, left-hand side of the V stuff. In a traditional approach, it's just a degenerative process, degenerative form of the iterative handoff, where you only do one iteration. In iterative form, you can do this repeatedly. Typically, it's organized around some number of use cases. You hand that off, so the downstream engineers can get started on those capabilities. And then system engineers go off and define some additional capabilities. And so you can do this incrementally, as well as at a singular monolithic traditional style handoff. And the process itself doesn't really change in terms of how you organize it, what you do, what you hand off, and the work involved. But it's a question, do you do it once or do you do it many times? The recipes involved in the handoff, there are several different recipes. And so you shouldn't think of the handoff of system engineering as a point in time. But really, it's a workflow. And this workflow can take a few days for a small system, up to several weeks for a really large-scale system. The workflows are discussed in my recent book, the Agile Model-Based System Engineering Cookbook. These workflows include preparing the system engineering model for handoff. Because there are particular sets of engineering data you want to hand off, structuring your model to facilitate that handoff just makes life easier. So I tend to use that as a driving criteria for how I organize my models to facilitate that handoff, and we'll see examples of how a model can be handed off to do this. When you hand off, you create a federation of models, starting from the system engineering model, but including a model per subsystem, a model for kind of shared physical interfaces and physical schemas. So it has a set of models that gets federated. So we'll talk about how to do that. Most of system engineering, at least the way I practice it, we focus on logical interfaces. We focus on the content and the data around the interfaces. And we focus a bit less on their physical representation, what I call bits on a wire. But when you get to the handoff, you do need to have bits on the wire defined, because now these teams, these subsystem teams are going to go off and they're going to build physical systems that they want to connect to other physical systems. So to do that, they need to understand what are these physical interfaces. So converting the logical to the physical interfaces is a big part of what goes on during the handoff. Deployment architecture is the arrangement and connection of contributions from different engineering disciplines. The contribution from an engineering discipline is, we'll call a facet, like it's a software facet, a mechanical facet, electronics facet, and so on. And the deployment architecture is identification of the contributing facets, how they connect, how they exchange stuff, information and flows and energy and so on, and how they are allocated responsibilities. We call that the deployment architecture. So we have to create that. We want to understand and characterize the interdisciplinary interfaces. So how do they, I tend to focus on how the software and electronics collaborate, but there's also electronics and mechanical aspects and hydraulics and pneumatics and other aspects as well. Those need to be defined. And of course, we have to take our subsystem level requirements and decompose them and allocate them into these engineering facets. So the software folks know what they need to do, the electronics folks know what they need to do, and mechanical folks know what they need to do. So everybody is clear what their contribution is to the overall functioning piece that they're working on and the scope of the system. I mentioned logical interfaces, this is where we focus on the logical properties, the content, which is information and ranges and accuracy and precision required, reliability, it's kind of logical properties and characteristics. And we care less about physical representation, what I call, again, bits on a wire. But we'll need to get to that representation as a part of this process for the handoff. And as I mentioned, an engineering facet is just a contribution of a specific engineering discipline to the design implementation of a system. So prerequisites to do the handoff. What's true before we do the handoff workflow? And that's what this block diagram is kind of trying to schematically show. So first of all, we've got a system functional model organized around use cases, right? The system level use cases. These trace to typically shell statements, individual requirements, and you can have interactions, you can have user stories, you can have detailed state machines, activity flows, describing, refining what we mean by that capability or use case. Then we have an architectural model, which could be in the same project that we have, where we have subsystems, the large-scale pieces of the system identified, and how they work together to form the overall system structure. These also trace to requirements and trace to potentially subsystem level use cases. Now, if you have a trivially simple subsystem, you may not have to have use cases. You got 5 requirements, but you might have 1,000 requirements for a subsystem. In which case, it might behoove you to organize it into use cases, and from there you can drive down into the scenarios, the user stories, and state behavior, and so on. But you got some sort of specification of how you want that subsystem to behave and perform its job. Subsystem itself, another piece of the architecture will be the logical interfaces, how the system connects to things in its environment, and how the subsystems connect to other subsystems. And we're going to define those primarily using logical interface specifications. These type the connection points, which are the ports on the subsystems. And so using ports allows the interfaces to be first order citizens for discussion. But they're still defined in terms of logical interfaces. These logical interfaces include, service specifications. One of the things that I do when I do logical interfaces is between these high-level pieces, whether it's the actors or to the subsystems, all of the information, all the service invocations are done asynchronously. It just simplifies the execution, simulation, rendezvous. I don't have to worry about concurrency semantics and blocking and all that stuff. I can just focus on the exchange of information. And so I model them as signal receptions that possibly carry data. We will have to convert that into other kinds of physical communication later on, and we'll do this in the handoff. But those are the service specifications. For between these elements, they're going to be signal receptions that carry data. Internally, the messages to self, internally, there might be operations to do that, which are synchronous. But the signal receptions are asynchronous, it just simplifies the rendezvous. Then there's flow specifications. In software, when I'm doing software work, I typically don't have flow specifications in my interfaces because that's not how software works. Software works by invoking services, and the services carry the data. And that's what I actually typically do for software, except where I'm modeling explicitly data-centric middleware like DDS, in which case I might have flow specifications that map to the subjects in a DDS schema. So, but most of the time it's just services of some kind. The data that's defined that goes across those encapsulation boundaries and used in the interfaces need to be defined as a data schema. It's not enough to say radar track. You have to say, well, what constitutes a radar track? Well, we've got a position in 3D space. We have a velocity in 3D space. We've got a range. We've got acceleration. We've got a comet ID. We have characteristics about it logically, right? And that's what we want to do is characterize that in terms of this logical data schema. We will have to refine that later in physical schemas when we do the physical interfaces. I'm a huge believer in using units and quantity kinds here and specifying metadata as part of the interfaces, including things like latency and precision, accuracy, fidelity, reliability, and so on, because these are properties you want to be true of the implementation, but they're still logical properties. Okay, so that's the starting point to do a handoff. Now, if I'm doing this incrementally, I'll have, suppose there are 50 use cases in the system. The first handoff might have 3 to 5. Next handoff, has another 3, 4, or 5 use cases. And so you can do this incrementally as well. You don't have to just hand off all 50 at once. Depends on what is your underlying engineering process in place. And this works for both of those. So I talked a little bit about model organization. How do we organize the models? Well, in terms of the architectural design part, which is, I'm talking just about the parts relevant to the handoff per se. There are other parts that I won't talk about here. So this is the architectural design package, where we've got the overall architecture shown, the system blocks and so on shown, and views of that. Inside, there's a nested package of decomposition, with ultimately a package per subsystem. These form what I call the subsystem specifications. And the reason why it's organized that way is later on during the handoff, when we want to hand off to a particular subsystem team, they want to be able to reach in and grab all of the stuff that they need. This simplifies reaching in and grabbing what they need. They don't have to scan over the entire model and look for stuff. It's organized neatly for them to grab stuff. The other primary part of the model, systems model that's relevant is the interfaces package. Again, these are logical interfaces. I typically use proxy ports for the connections among the elements. And so we have interface blocks that define those sets of proxy ports. And each one of them has internal service invocations and flows and so on, interface stuff. And the data types package identifies the data schema of the information that's passed along in these interfaces. So that's how I organize the model to facilitate this handoff. And then there's a couple of workflows here that go on in parallel. The first task here is to gather the subsystem specification data. And if you organize the models in the way that I did, then they're kind of pre-organized. There's no work to do. If you did something else, then there's possibly work to do to grab all the stuff and bring it together. So there are two parallel flows. In the left-hand flow, we're going to create what's called the shared model. So we're going to create a federation of models. And one of these is the shared model. The shared model's purpose in life is to serve as a shared repository for common information, such as interfaces. Kind of by definition, interfaces are common things because there's at least two parties that care about them. So that's why it's called the shared model. I'm looking at the structure of the shared model in a little bit. And then we also then take the logical interface specifications and derive from their physical interfaces and physical data schemas from that. On the right-hand side, we do a subsystem model per subsystem. So if there are 10 subsystems as the large-scale pieces of a system, we'll have 10 of these models, one per subsystem. So we create a basic kind of standard structure for that model. We'll see what that looks like in just a minute. And we reach in and grab the specification. Then we want to define what are with the deployment architecture, basically, the interdisciplinary interfaces and responsibilities, and define how they collaborate, these facets collaborate. And we also want to allocate the requirements allocated to the subsystem into the engineering disciplines. And to a large degree, it'll be take a subsystem requirement, or system requirement, from it derive facet-specific requirements. The software has to do this, the electronics must do that, the mechanical system must do that, the hydraulics do this, and so on. And then allocate those to those engineering facets. Do this for all of the subsystems. And that then constitutes the handoff. This is typically led by a system engineer or a system engineering team, but it also has representation from the subsystem teams and the individual facets contributing as well. What you don't want is the electronic folks defining the software interfaces. That's just a bad idea. or the software engineers defining what the electronic interfaces look like. This should be a collaboration. And that's the point of this interdisciplinary product team. So then you create a set of models. So this is a snapshot from the Rhapsody tool. So there's a Harmony SE profile that Andy Lapping and I authored for the Rhapsody tool. And his has automation to create these. So it can actually scan over the model and say, oh, you've got these subsystems. I'll create a shared model. I'll create a model for subsystem. I'll give them basic structure. I'll set up the reference links back to the other models. I'll do all that for you. But if you don't have automation, it's not that hard to do by hand. It's not, it just saves you a little bit of time. But this is then this set of models that you'd have. In this particular case, which is the ACES system, it's the air surface control enactment system. So it's managing the control surfaces for attitude management on an aircraft. So you might have like 30 years of these surfaces on an aircraft. And you see these subsystems, like there's a surface control surface subsystem, hydraulics management, power management. There's the shared model and so on. So all these different subsystems that you'll find for these. So the federation of models looks kind of like this. We start off with the system engineering model. And we've seen the organization like this. We've seen the interfaces and types. We've seen the subsystem specification models. We saw that before. The little triangle here indicates that it's a model, not just a package. And the interfaces here, again, in the system engineering model are, by and large, logical interfaces. In the shared model, we will refine those into physical interfaces. And same thing with the types. The types goes into common types. These will be refined into physical schemas. So here you might define something as a unlimited natural. This will be a scaled 32-bit integer, right? So it's a more physical representation and using big Indian format or something. So some physical representation. Subsystem specifications then are imported into the subsystem models as kind of one of the starting points for them to begin their work. To define the deployment architecture, interdisciplinary interfaces, allocate requirements, and then proceed with the engineering development. There's also this domains model that's used later in the process. Domains are hold shared design elements. So as these subsystem models create design elements, if you want to put them into the library so they can access them and reuse them, they go into subpackages inside domains. That's what it's there for. At this point, it's just a placeholder. Okay, so modeling physical interfaces. Let's talk a bit about that. So the logical interfaces, again, as I mentioned, are done as service specifications using signal receptions in interface blocks. Largely, that's what I do. So you might have a navigation, the radar subsystem, have an event, here's a radar track, and it passes a radar track. And in the physiological data schema, then we define what are the aspects of radar track. I need, a range up to 500 miles. I need a plus or minus 10 meters. I need latency of no more than half a second. Latency, whatever the properties are. But physical representation, and this might be on a 5053 bus message, with low-level bits in a particular order, bits on a wire that mean something. So I have to go from the logical to this physical representation. To do that, we first of all identify our protocol. If you're using a standard existing protocol like 1553 or TCP or whatever, reference that. Okay, that's what we're going to do. And that forms kind of the lower tiers of the ISO protocol stack. So certainly data link layer, session layer, that sort of thing. That's where that's defined. But those don't define the application layer, layer 7 in the protocol stack. And that's where I want to say, I want to send a command saying, move my control surface to plus 4 degrees or to minus 2 degrees. That's part of the application protocol. And we have to create messages that mean that in the application level protocol. And that's what we're going to create here. The lower data link and network layer stuff is already defined by the protocol, unless you're defining your own protocol, which I've done that too. So we identify a protocol. And then we specify this application level protocol for every service or flow in all the interface blocks. We need to define how is that realized in the protocol if we're doing protocols. There are other ways to do this as well. Voltage levels and energy flow and exchange. There's a bunch to do it for other kinds of things. Specifically, I'm just talking about protocol implementations here. The Harmony process, or Harmony work profile, contains a stereotype called represents, which we will use to trace back from our physical representation to our logical representation. So you could use refine for that. Refine, I think, is subtly different. And refine doesn't cross abstraction layers. And this really does cross abstraction layers. So I created another stereotype called represents. If you want to use refine, I wouldn't yell at you too hard. But we need one to have a correspondence so we can demonstrate that all of the logical interface pieces are represented appropriately in the physical interface schemas. And then we can create tables and different views of that, create the ICDs. I talked about ICDs before in previous talks. And then we can review that. So this is kind of what we're going to do to create the application level protocol and map these to messages in our protocol. To do that, I have a set of standard stereotypes that I use. They're part of the Harmony SE profile in Rhapsody, but they're not hard to create. A couple of really relevant ones. Some of the ones are just used to mark. That's a software thing. That's a mechanical thing. So we've got some just identification style stereotypes. They don't carry additional metadata. But bitmapped and byte-mapped are particularly important because they do have all these tags, so you can identify the meaning, usage, orientation, timing, and other properties of these bits in the case of bitmapped, or of the byte in terms of byte map. So in terms of bitmapped, we've got some tags like how many bits are involved, where do you start in the bit mapping, any kind of timing constraints, how do I use it, and then you get a definition for every bit for the type we're applying it to. For byte map, we identify Indianism, any format information you might want to add, how many bytes are involved, start address, if that's appropriate, units involved, and usage, and so on. So other kind of metadata information. That'll be from, again, parts of the interface definition for the physical interface. So here's an example using bitmapped. We've got this sample class, and we see a status field, which is unsigned character. So it's just like 8 bits, right? 8 bits. But the bits all have meaning, because that's how it's encoded in, for example, in the hardware. And so bit 0 means if it has the value 0, when you read it, everything's fine. And if it's 1, then it's bad. You should look at the error code. Bits 1 and 2 are which channel is involved, and 3 to 7 are a 16 up to 0 to 16 valued error code. So, and that's what this is defined to be. And these are the values of these tags. For the byte mapped measure status, it's also a character, 8 bits. And you can see how this works in terms of usage. Write any value to the measure status register, and this status information will appear at the status field register. That's what is defined here. And then there are characteristics, for example, at the start, the address you're going to write to is located here. So now we specify the actual physical bits that represent the logical information. Yeah, realize isn't, there's a question about realize. Realize isn't exactly appropriate. Realize is basically providing implementation of a specification. And this is different because it's crossing abstraction layers. So realize doesn't quite fit. There's some baggage associated with realize, that the technical baggage to carry along with it. Okay, so here's an example of protocol. So I invented a protocol for this called Control Bus Message Protocol, CBP protocol. And this is the basic structure for the base class for the message. There's a command byte, and there's a length, how many bytes are involved. There's a CR 16-bit, 30-bit rather, CRC, sender ID and receiver ID. Okay, and this is just basic message, and these are used directly for messages that are going to send logical message, but don't have any data payload. Just want to send a start or stop message. I just got to send the message where the command byte is start, and the command byte is its enumerated value. Other messages are subclass because we're going to add data payloads. So for surface configuration, remember this is a control surface for a wing flap or aileron. Some of the control surfaces have a trim tab. Some of them extend and retract as well as rotate. And so you specify minimum, maximum rotational values, trim positions, extensions, and give it an ID. So there's a message you can send to the particular control surface. These are the ranges we want you to check on. This is your ID and so on. So use that in further communications. So there's a message for that. There's another message you get state. And this is used in some of the messages like display state message or get status message. So these are also subtypes of the base message, but they add additional payloads for carrying information around. That's what we mean by the application level protocol. So once we've done that, we can create tables that kind of summarize information and put these in an ICD if that's what you'd like. So this is just another Rhapsody table. So we've got the messages here. We see CBP move, for example. We see it represented 4 times because ultimately there are 4 different things we're showing with regard to that. So move has an attribute called position. That's a piece of data that gets passed in that message. Position. And we see it's a double. Its type is double. That's the 3rd column here. And then there's also metadata held in tags. It's going to be 4 bytes. We see it's going to be 4-byte IEEE format. And it's going to be basically commanded position for CPP move. There's also another field in the message, which is surface ID, which one of these IDs we're talking about, where that's an enumeration. So this table basically lists all the messages and all the data that gets passed in these messages. You would like to have relationships, traceable relationships between the physical messages, the scheme that you came up with, and the logical messages that are parts of the interface blocks from your SystemL systems model. To do that, I use this representation relationship. The Harmony SE toolkit profile has some automation for that. So you can select, for example, a protocol class, and you can apply it to a bunch of different messages and add these are all receptions, event receptions, right? Signal receptions. So all of these are applied. So it's just an applicator. You can also just do it by hand. It's not like it's super hard, but there is some automation built into the Rhapsody tool to support this. Once you've done that, then you can create basically a trace table, which relates the message in the interface blocks and the logical protocol and logical messages to the physical implementations. So here, for example, we see for the services, check power, request hydraulic status, enable request hydraulic status. Here's the position set, EV error, and so on. All of these messages, these signals you're sending logically as part of the logical interface, you can see what message they correspond to in the protocol. So the first few are just a standard off-the-shelf CBP message. Some of them are move, which is a subclass. Here's CBP hydraulic status for passing hydraulic information and so on. So these are the subclasses. And this shows the relationship between the set of services defined in the logical model and the physical realization in your communication protocol that you can implement. This table in Rhapsody is drawn up with a thing called context patterns, where you can define exactly what you want to show on your table if it's not a kind of a built-in feature. So there's this language, if you will, for specifying in detail what you want to show up in your tables. Now for the subsystems models, we have a kind of standard structure where, and this is created by automation or again by hand. First of all, we basically import our specification from the systems model into our subsystem model. That's kind of our starting point. Then the specification model is where we're going to do some of the design work. The deployment package is where we create the deployment architecture, which we'll see what that looks like shortly. Then there are references off to the requirements analysis package, so we can reference off to the requirements so we can trace to our specific requirements. That comes from the systems model, so we're just referencing the systems model there. Physical interfaces, that's referenced in the shared model, as along with the common stereotypes and the common types package. These are all in the shared model. One of the things we have to do is create this deployment architecture. So we have to identify what are the contributing engineering facets and how do they connect and what are their responsibilities. Ultimately, that's what we want to do. What I tend to do is there's what I call a dynamic connection. We're going to exchange information or energy or fluids or something. Then there's a port, and then we have connectors. If it's a static connection, I'm going to take this and I'm going to bolt it to that. It's really not a static connection. It's really not a dynamic connection. It's static. Then I tend to use associations and connectors or links. Depends if I'm talking about, blocks or parts or instance specifications, but associations and links are more the static connections. So this is kind of what I do. So here we have what I could call a deployment diagram. It's just a BDD or an IBD rather, or a structure diagram in UML. Where we've got, you see stereotypes here for software, electronics, and mechanical. This becomes just a holder for all the software in this subsystem. All the software is inside here somewhere. I don't really care about it. That's the software engineer's work. I don't care about the internal structure there. But I'm going to levy requirements on this. So all the software requirements will be levied to this element so they can track their requirements. Notice that there are connection ports, between this and the electronics. And those are defined by interfaces. And that's when we talk about how does the software collaborate with electronics to get stuff done. So if I want to set motor speed, for example, by writing to register, this defines how that's done. That's its point in life. That's what it does, is define how that's done. In this particular case, I did show a little bit of the electronic substructure, at least logically. There's a timer set of services, there's movement services, there's hydraulic control surfaces, and there's some sort of command communication services, maybe with a TCP/IP protocol or a CAN bus protocol, whatever it is you're using. So divide those up. You wouldn't have to do this. You could let, just stop at the boundary of the electronics block. But I went to one more step to show you can if you find that useful. Down below, we've got the mechanical block, where we're going to allocate all this stuff to mechanical engineering and then electronics. And here we see these connectors between these parts. These are the static connections. This is where I'm bolting stuff together. I'm going to bolt this motor, onto the mechanical frame, right? This is the mechanical connections. And then we got these interfaces that define what goes across these different connectors. Okay. And they're empty here, but because I'm just trying to show you kind of schematically how it's represented. And this is what I call a deployment diagram. Now, it's not a UML deployment diagram. UML deployment diagrams are horrible. That's why they're not in SysML, because they're really not very useful. But this is used to show deployment architecture. So your block diagram in SysML, IBD in SysML, or a structure diagram in UML. So we're defining the interdisciplinary interfaces. So here we've got our subsystem model, and we're referencing in our interfaces here. And here we've got an interface, between the software and the electronics for the timing services. And we see this is the timer register, timer control register. We've got some services like zero the timer, start the timer, stop the timer, read the timer. So we've got some services here as well. These are all memory mapped, which means they're hardware registers in the memory space that we'll read and write to make things happen. So for zero timer, which is some functionality, basically we write a 1 to bit 0 in the timer control register to start the timer, or excuse me, to zero the timer. For timer control register, we see that there are all these different bits. There's a zero timer bit, there's a start timer from 0, there's a stop timer, and bits 3 to 7 here were unused. So again, we characterize what the interface is between the software and the electronics. And then we can build a table of that information. So here we see the control register as part of this table, as part of the interface, as a control register, as part of the interface. And we can see all of the tagged values, the number of bits or 5 bits that are used at this address, how do I use it, what do the bits mean, how should I interpret them, and so on. And I can put that in tabular form. And that forms the definition of the interface between the software and electronics in the context of this particular subsystem. For the requirements, we get handed, the subsystem team gets handed a set of subsystem level requirements. Now, some of those requirements can be directly handed, oh, that's a software requirement, or that's an electronics requirement, or that's a mechanical requirement. But probably most of them are really some combination of software, electronics, mechanical. So we have to create derived requirements from those subsystem requirements, which are engineering facet specific. And that's what this is all about. So we take a subsystem level requirement and we derive into that software requirements, a couple of electronic requirements, and this is a mechanical requirement. These then get allocated with allocation relationships to those software blocks we saw in the deployment architecture. So these requirements get allocated. So here's again the subsystem requirement. It derives into some software requirements, which then get allocated to the software block, or the electronics block, or the mechanical block. And these can be represented again in tabular form. So we can see that there's this requirement, a particular subsystem, and what it's derived from is a relationship, what it's pointing to. And that's basically what I do to the handoff. Once we're done with that set of work, we define the deployment architecture, allocate the requirements, then the software can start beginning to do their implementation design work. Same with electronics, same with mechanical, pneumatic, and so on. Because they know what they need to do, how it fits in the context of the subsystem. The interfaces are physically defined at this point, and they can go off and do their engineering work. In an incremental approach, they'll get another drop of additional capabilities sometime in the future in the next iteration. In a monolithic kind of traditional drop, they've got all the information for all of the interfaces. With that, I'll give control back to Ray and see if there are any questions.
Well, before we get into questions, we have the very distinct honor of being able to name the book winner, the one that will receive a copy of your book, your cookbook. And the winner is Douglas Junker. I don't have further information on him. I hope he is present. If not, we'll get the book out to him. We'll look up his information and get the book out to him. So, Douglas Junker, you're the winner.
Congratulations.
So, first of all, I'd just like to make a general comment in terms of, with regards to handoffs. I really appreciated your point in stating that it's more than just a point in time, and that you actually need to organize your model as to the handoffs that are required or that you're expecting to deliver it to. I also like the idea that you talked about it as being a federated model. Those are pretty high level concepts, but it's not just a matter of that you start at a point and you finish at a point, and at that time everything is supposed to come together. There is a question. There is a question here from Christopher Carhart, and it's with regards to would realize be an appropriate relationship when mapping logical to physical interfaces?
Yeah, I did address that. Realization is basically really strongly tied to generalization. So this is the type of that. Realization realizes it, but it provides an implementation, a detailed implementation. And that works if things are the same level of abstraction. But when you go from logical to physical, you're changing abstraction layers. And you can't necessarily do that. For example, let's suppose we've got, here's a radar track, but the realization will be a set of messages, not just one message, but a set of messages in a particular order carrying different data fields, data payloads to achieve that same goal. So realization would say you've only got one thing. It's structured this way, you've got one thing, which is the realization of that. But really, it's a collaboration of these things, which collectively realizes it. So realizes doesn't quite work when you cross abstraction levels, because you have to impose the same overall structure on the thing into which you're realizing. So it doesn't quite work, and that's why I use represents.
Well, this might very well lead into the next question, Bruce. How do you set the boundaries between software and electronics? Meaning, how do you decide if it's a software requirement or whether it's a firmware requirement?
That's an interesting question, because firmware is kind of like software to my mind. To my mind, it's software. But electronics is when you if you can build it with a soldering iron, it's hardware. To my mind, electronics, right? Or chips. But as soon as you start doing things programmable, I think of it more in terms of software. But I agree that there's a grayness there. So you can decide for your project what makes the most sense given your engineer's skill sets and their assigned responsibilities, whether you want to call something software or hardware. So it's kind of up to you. And to some degree, it kind of doesn't matter. But you want to be clear. If we have got this definition of what electronics means, then this is what you need to know. This is your responsibility. So it's clear. What you don't want is to have a requirement which is partially met by software and partially met by electronics, both allocated to different elements, because they don't really know what's the overlap. Am I doing all of this? 2/3 of it? 7/8 of it? They have to know precisely what their responsibilities are to make sure that it works together. And we're just trying to avoid ambiguity here. And that's the point of doing the allocations of the engineering disciplines.
Yeah, I think you bring up a good point there, Bruce. Maybe some of it depends basically on the capability of the team or that you're handing it off to. When we talk about firmware and embedded systems, whether the person is an engineer and understands the hardware side and then is doing the firmware, or whether they come from the computer science side and maybe don't have that understanding. And so depending on who it is that you're reaching out to, it may require a slightly more elaboration on one side or another.
Right, yeah.
How do you explain the distinction? Sorry, my screen just jittered. How do you explain the distinction between logical architecture and physical architecture? Do they overlap, or are they completely distinct?
So I think that kind of at an abstract level, physical includes logical, because logical focuses on what is the nature of the information. So in logical, I've got an interface to my radar. I'm going to have a radar track, right? And I want to say, well, I want to have range. Well, I want to logically describe what I mean by range. I don't care if you do integers or 4-byte IEEE formats, or I don't care about the format. What I care about is I can support the range appropriate. So anywhere from, say, 100 meters up to 500 miles, let's say. I have support for the adequate precision, plus or minus, 10 meters of accuracy. Latency, I have to have an answer within half a second, and those kind of logical properties. Physical interface kind of includes all that. Plus, we say, and we're going to use the 1553 bus message. It will be sent, on this kind of a schedule. It'll have these bits on the wire, first this bit, then that bit, then that bit. So it includes that logically. It's a little more complex than that, but that's the basic idea, that physical adds additional information. And the reason why we focus on logical is because, well, one, in the system engineering model early, we don't necessarily know the implementation technology. But even if we do, it obscures the process for determining all of the important properties, just for the sheer mass of detail you're managing. So we focus first on what is essential for correctness and what can I defer later. So if I want to pass some value, I can use maybe a 32-bit integer, scaled, take the actual raw value, multiply times 100 to get rid of the 2 decimal points and pass that. Or I can use an IEEE floating value, use maybe an enumeration. We don't care the actual, how we're going to send the bits on the wire. What we care about it is its logical properties. So I hope that answers the question.
Okay, there's another question here. Do you stereotype derived requirements in your profile? And is there a place you have the profile documented?
Yeah, in the ICD, if there's some presentation on my website, there's some discussion of it. It's certainly if you have Rhapsody tool, you get it when you buy Rhapsody. So for derived requirement, of course, that's a standard relation. I do add stereotypes. If we go back to this slide, the list of stereotypes, where that was, here we go. So if I want to identify this is a software thing or electronics thing, I play the stereotypes, and they're just for when I have derived requirement. It of course has stereotype requirement, but I also add the stereotype software if it's a software requirement. Just the table, that's a software requirement or electronics requirement or mechanical requirement or hydraulic requirement. So I do that more for just so I can build in different tables if I want to and manipulate in different ways. I can track down the collection of software requirements. So just tagging it somehow with the stereotypes allows me to identify those things easily when I need to.
Okay, Bruce, this is the end of the questions that we have. So we look forward now to your sessions in January. 2 more sessions, the last 2 sessions of this series. And thank you very much, Bruce. We appreciate your session today.
Well, you're very welcome. If you celebrate Christmas, have a nice Christmas. It's coming up. And I'll see you in January.
All right, then. With that session, we complete today's webinar.